This is our part 2 of 4.3. In this particular part, we're going to talk about concavity and inflection points. So in part 1, we talked about intervals on which a function is increasing and decreasing, right? Local extrema. And if you forgot, I'm going off this handout right here. Okay, this is posted on Canvas again. I will have a link next to the file or the video file, and it will also be found under the files tab. So we're going to be looking at this particular part right here, concavity, and we'll work out a few of these problems right here. So what is concavity? Well, if we look at a graph, I'm going to draw it out. Just a random curve, okay? Like say we have something like this. Just making up something like that. Now, of course, from 4.3 part 1, where we're talking about where a graph is increasing and decreasing, well, we know that we are decreasing, along right here, right? Because if we read a graph from left to right, we're going down the hill. Also, we're decreasing right here. And then we could also say, oh yeah, we are increasing along that portion, right? And we're also increasing along this portion right here. And remember, increasing and decreasing are always done with respect to x, correct? Now, what is concavity? Concavity is basically kind of like, does our graph open up or down, or does it create some kind of bowl shape, bowlish looking shape? So I'm going to change this. Right. Oh, no, I'll leave that the same. What I mean by bowl shape is if we look at this chunk right here, this chunk of stuff, just to there, okay? This blue bowl that I have that's opening up, that's concavity right there. This is concave up. And I keep saying bowl because that's the easiest way to visualize it, okay? So this is something that holds water, right? Like you got a water bowl or a cereal bowl. And then if we look at this piece right here, the green, that's concave down. And that's because it's basically an upside down water bowl. Now, one more important piece is right here. That little, I'm going to draw it with orange, this little part right here. The second where it transitions from different concavities, meaning whether you go from concave up to down or down to up, that point where you transition from one different concavity to another, that's called the point of inflection. So basically, inflection point is where you change or where concavity changes. So again, it can be from up to down or down to up. The order doesn't matter. It's just that instant where it changes, or the bowls change like that in that case right there. How do we find concavity? Well, it's all done via the second derivative. Okay, remember the first derivative of a function gave us the intervals on which a function's increasing or decreasing, right? And then from there, we could also determine local extrema, right? Like that would be a local min, that'd be a local max in this case right there. And you'd set the derivative to 0 and solve for x, and that would give you those values, right? And then we would choose test numbers around them, right? Something smaller than them, in between them, a little bigger than them, and plug those back into the derivative and see the sign to determine whether it's increasing or decreasing. Concavity works in the very same fashion, except that we're doing all that stuff with the second derivative. So coming back to these notes, concavity, the property of curving upward or downward. And look right here, it says, oh, if the second derivative of the function is greater than 0, meaning it's positive, then we say that that function would concave up. Or if the second derivative is negative, then we'd say it would concave down. The point where x changes concavity, right, what I wrote right here, is called the inflection point. So how do we figure this out? It's the same exact process that we did with figuring out intervals where it's increasing or decreasing. It's just that instead of doing the first derivative and choosing test points, you're using the second derivative and choosing test points. Okay, it's the same exact thing. Let's try out, we'll do 7 and 8. So right here, what we want to find is the inflection points and concavity, okay? So to find inflection points and concavity, you have to take the second derivative. Well, to do that, we got to get to the first derivative first, correct? So the first derivative of this function is 3x squared minus 12x. Don't stop here and set it to 0, okay? You would do that if they were asking intervals on which it's increasing and decreasing in local extrema. But right now, we're just being asked for inflection and concavity. That's second derivative information. So we take the second derivative, we get 6x minus 12. And if we set that equal to 0, we have x equals 2, right? So let's see what happens right here. Where do we go from here? Well, remember, just like with the first derivative, when we were finding intervals of increasing and decreasing, those values that we got were the critical values. And this is very similar. So 2 is kind of like a critical value right here. And again, what we're going to do is we're going to test, right? We're going to test random numbers within these regions right here. So like in region 1, we can test anything less than 2. Like I'll test x equals 0, right? Or you can test -1, 1, -18. It doesn't matter. In region 2, something bigger than 2, I'll test x equals 5. You can test x equals 3 on your paper. Ultimately, what are we looking for? Just what's the sign of the second derivative going to be when we plug these test values in? So really important with these test values for inflection and concavity, you're going to substitute them into the second derivative, not the first derivative or function, okay? Or the original function. For concavity and inflection points, all that stuff deals with the second derivative. So if we plug 0 in to our second derivative, remember this is it right here, we just want to see, do we want it with a positive value or a negative value in the end, okay? So that we have 6 times 0 minus 12. Well, that's easy to see that that's -12. So that just tells us to the left of 2, we're concaving down because you have a negative value, okay? If I test x equals 5, we get 6 times 5 minus 12. Well, that's 30 minus 12, and that's 18. But what matters is that it's positive. So what does that tell us? It means to the right of x equals 2, you would have a bowl that would be opening upward. To the left of 2, you'd have a bowl that would be opening, you know, downward, right? Upside down cereal bowl. Now, wherever you have a sign change, when we go from negative to positive or positive to negative, that's a point of inflection. If for some reason both of these were like negative, negative, or positive, positive, then you will not have an inflection point. In order for an inflection point to occur, you must have a sign change. So it has to go from negative to positive or positive to negative. So in this case right here, we're going from negative to positive. We have an inflection point at x equals 2. But what about the y value, right? We need a point right here. We need an actual point. What does a point have? An x and a y value, right? So y is equal to f of 2. And take that 2, right? And we're going to plug it into the original function. And when you do that, you get negative 14. So your answer is 2 comma negative 14. That's the inflection point right there. Remember, point always has an x and a y. Now we need to figure out concavity, the intervals of concavity. Basically, where's it opening up? Where's it opening down? So concave up and concave down. So it's concaving up wherever you have the plus signs, right? Just like how we did intervals of increasing, you look for the plus signs, right? So where did it begin to be positive, or you have the plus signs at starting at x equals 2? And you're going to have parentheses around these numbers all the time, just like with the increasing and decreasing. And until what x value does it continue to concave towards? Well, towards further to the right is positive infinity. Okay. Where is it concave down? Well, the smallest x value that it starts to do it from is it's not 2. What's way off forever over here? Negative infinity. So beginning at negative infinity with respect to x, it begins to concave down until what x value? 2. Just like that. So very similar, right, to the increasing and decreasing. Very similar. It's just that you go into the second derivative and you're running through the same steps of choosing test points within your region. Don't forget, though, you have to plug those test values into the second derivative, okay? I keep saying that because people will plug them back into the first derivative or the original function. No, no. The only time you plug in the original point back into the original function is when you need that actual point, like when they asked for the inflection point, right? That's when we plugged x equals 2 back into the original function. Or where they asked, where's the local max or local min? That's when you plug those critical values back into the original function to get the x and y value right there. So let us try the next one. So number 8, that says f of x equals 2 plus sine of x. And then on 0 to 2 pi. So we're looking for inflection and concavity right here. We need to take the second derivative. So we got to start with the first derivative, that's cosine of x. And then second derivative. Remember, derivative of cosine is negative sine of x. So now we need to take that and set it to 0, right? So where does negative sine of x equal 0? Well, you can divide by -1 if you really want to, right? And then we have sine of x equals 0. Where does sine of x equal 0 within this domain restriction of 0 to 2 pi? Well, it comes back to the unit circle, right? Where is that happening at? This is 0, right? And if we do 1 full revolution, we wind up back at 2 pi. But where does sine of x equal to 0? Well, right here. what is that value right there? That's pi, right? Sine of pi is 0 because this is negative 1 comma 0 right here. So in this case, we have one value, and then we're gonna have our, two regions again. We need to test, and it's trapped right between 0 and 2 pi. So we can't choose like negative values in the first region, or in the second region, I can't test like 10 pi, for example, because that lies outside or beyond 2 pi. So what are some nice values between 0 and pi, or pi and 2 pi? Well, something nice between 0 and pi is pi over 2, right? This is pi over 2. Let's use that. What's something nice between pi and 2 pi? Well, 3 pi over 2. And of course, there's all kinds of other ones, right? Like you could use 5 pi over 4 if you want to, 7 pi over 4. Anything between, like right here, is totally fine, right? Now, if we plug these in, remember we're plugging them into the second derivative. So remember the second derivative was negative sine of x. And all we're trying to see is if we plug in these test values, are we going to get a positive value or negative value in the end? So if I say negative sine of pi over 2, what do we get? Well, what's sine of pi over 2? Sine of pi over 2 is 1. So this is negative, and then times 1, that's negative 1. Remember, I'm just dropping this negative down right here. So that tells us that anything within the first region is negative, or that would be concaving down between 0 and pi. What about negative sine of 3 pi over 2? Well, sine of 3 pi over 2 is negative 1, but you have a negative on the outside, so you have a negative 1, which is positive 1. That tells us that this is positive right here. Okay. So let's look at what we have. Do we have an inflection point? Yes, we do, because we have a transition in the second derivative from a negative to a positive. Remember, as long as you have that, you have an inflection point. If these were both negatives in both regions or both positives, then we wouldn't have an inflection point, okay? But yeah, we do at pi, at x equals pi. But what is that as a point though, right? What do we need to do? We need to figure out what is the respective y value when x is pi. So we take this and we plug it back into the original equation. So y equals 2 plus sine of pi. What's sine of pi? That is 0. So that is 2 plus 0, which is 2. Your answer is pi, comma 2. Now, what about concavity, right? I'm just going to put CU for concave up and CD for concave down, okay? Concave up, concave down, concave up, concave down. Where is it concaving up at? Where you have the plus signs. In this case, it starts at pi, right? And it ends at 2 pi. Be very careful. These, usually the trig ones don't go to infinity because they define it between something, okay? And remember, concavity always has parentheses around your intervals, just like increasing and decreasing, same thing. What about concave down? Concave down is where you have the minus signs, all right? So concave down is just from 0 to pi. Now, what if we throw all this together, right? Like we have a problem where we want to figure out intervals where it's increasing and decreasing, local extrema, inflection points, concavity, all that stuff. That's the next set right here, right? I'll do a few of these right here. All right, so if we look at this, right, we want to find out intervals of increasing and decreasing and local extrema. Well, how do we do that right there? That involves the first derivative, right? This is basically incorporating all of 4.3 together. Before I do that, though, before we start taking derivatives, we should always write our problem in descending order. This one's not in descending order, right? We want the highest power first, and then, you know, the next highest, and so on. So if it's not in descending order, put it in descending order. So this is f of x right here, right? Notice I didn't change the signs. There's still negative x to the fourth, still positive 6x squared, and still positive 18. So now let's figure out that derivative. Looking at this one, you could do it from here, but it's just, again, we want it in descending order because it looks nicer and it's easier to work with. So if we put this in descending order and we take the derivative, we get negative 4x cubed plus 12x. Now remember, we're trying to find local extrema and critical values, and that increasing and decreasing stuff that involves the first derivative, right? So what do we need to do? Set this to 0. Now, where do we go from here, right? How do we solve this for x? Well, let's pull out a GCF. There's a GCF of negative 4x, right? And if I pull that out, I'm left with x squared minus 3 equals 0. And then we set both of these to 0, right? Remember, these are critical values, CVs, for increasing, decreasing, and extrema, right? That means local max or min. That's the first derivative stuff. So one of our critical values is x equals 0, right? This one, when you solve it, we get x squared equals 3, but then you have to take the square root of both sides. So what do you wind up with? X equals plus or minus, and then the square root of 3. So we have 3 critical values right here, right? We have 0, and then negative root 3, and then positive root 3. And now we have 4 regions, right? 1, 2, 3, and 4. A bunch. So we got to test 4 different values, right? So something less than negative root 3. Remember, root 3 is like 1.71. You can convert these into decimal. So if we test like negative, whatever, negative 4, for example, right? We'll do that. X equals negative 4. Something between 0 and negative root 3, we'll use x equals negative 1. Right here, we can use positive 1. And then for the 4th region, we can use positive 4, right? Again, you could choose any value within those regions, right? And we'll come up to the same conclusion of, oh, is it positive or negative when we plug those values into the first derivative. So let's test that out. Like test, if I say x equals negative 4. So remember, we're going to plug these into the first derivative, right? Right here. We just want to see, do we wind up with a positive or a negative value? So f prime of negative 4 is negative 4 times negative 4 cubed Or actually, I use a factored form. Sorry. That's easier to use, right? What do we say that was? This, right. So f prime of -4, I'm going to plug into the factored form. Remember, you can plug it into either one. They're both the same. It's easier just to plug it into the factored form. And again, what do we care about? Whether it's just positive or negative. So right here, if I go negative times a negative, -4 times -4 is positive. And then what's -4 squared minus 3? Well, that's 16 minus 3, which is still positive. So we wind up with a positive value. That just tells us in the first region, we are increasing. Now, what if we do it for the next region and I test f prime of -1? Well, we have -4 times -1, and then -1 squared minus 3. What ultimately happens right there? -4 times -1 is a positive value. -1 squared minus 3, that's 1 minus 3, that is a negative. What's a positive times a negative? It's just a negative. So right there, we know that in region 2, we are decreasing. What about for x equals 1? So f of 1, that's -4 times 1, and then 1 squared minus 3. So again, negative times a positive, this times a negative. 1 squared is 1 minus 3 is -2. That's a negative. What's a negative times a negative? A positive. If you want, you can figure out the numbers, and crank it all out and get some the values. But again, all that matters is just the signs. And if we do the last region, f prime of 4, we get -4 times 4, and then 4 squared minus 3. So negative times negative times a positive is a negative. And then 16 minus 3, that's positive 13, but that's positive. What's a negative times a positive? It's a negative. So we have this right here. So now where are we increasing from and decreasing? So remember, increasing is all the plus signs within the first derivative that we were testing. So where's the smallest value that we begin to increase from? It's negative infinity, right? So from negative infinity to -√3, and then also 0 to √3, right? Because we have another positive region right there. Where are we decreasing from? Well, starting at -√3 to 0, and also √3. I remember this goes forever to the right towards positive infinity. So there's our increasing and decreasing, right? Now, what about local extrema, right? Do we have a local max or min? Well, we do, right? Because remember, what's happening conceptually right here, from plus to minus, it means your graph is going up and then down, right? Because the slope's increasing, then decreasing. Right here, it's decreasing, then increasing. Right here at √3, it's increasing towards √3 and then decreasing once we cross it. So yeah, we definitely have some local maxes and mins. So local max. Remember, whenever you have Homestead open up, I'm sorry, down like that, that's a local max, local max. So you have a local max at x equals √3 and -√3, right? But we got to figure these out as points right here, right? So what is the respective y value for root 3 and negative root 3. Well, what do? We plug these back into the original. So we need to find f of root 3. We also need to find f of negative root 3. And we're going to plug them back into the original equation. So either one, right, of these two, because they're the same exact thing. Just watch the signs. This says negative x to the fourth. This is negative in parentheses root 3 to the fourth plus 6. And then root 3 squared plus 18. When you substitute all that in, what are you going to come up with? You come up with 27. Same thing with this one right here. Watch the signs. It's negative and then negative root 3 to the fourth plus 6. Times the negative root 3 squared plus 18. And you also come up with 27. So as a final answer, right, you would say, oh, we have a local max at root 3, comma 27, and also negative root 3, comma 27. And we had that other hump, right? I erased it at 0. So that was the local min. Local min at x equals 0. Remember with the number line that I drew right here, local min, we had a hump that was opening upward. So that would have been a local min at x equals 0. We also need to find its respective y value. So we need to find f of 0. Remember, these go back into the original function. So you're going to have negative and then 0 to the fourth plus 6 times 0 squared plus 18. That's just equal to 18. What is that as a point? That is 0, comma 18. So that's the first part of the problem, right? Or first little chunk. What do we do from here? We still have to find concavity, right? That's the second derivative. So let's go back to our f prime of x. Now we need to find f prime prime, right? Or the second derivative. What's that going to be? That's negative 12x squared plus 12. Let's take that now and set it to 0. But what can we do right here? We can take out a negative 12. If we do that, we're left with x squared minus 1 equals 0. And then we can divide both sides by negative 12. And now we have x squared minus 1 equals 0. So from here, what can we do? Factor. So we get x equals negative 1 and x equals 1. Remember, these are our critical values for concavity now. We can make a note, right? This is for concavity or to determine concavity. So now we have 3 regions. So remember, this is our second derivative right here. All right, so if we test something in region 1, I'll test x equals negative 2, for example, okay? If we plug that into the first derivative, I'm sorry. If I plug it into the second derivative, what's the sign of that going to leave us with? This is negative 12 times 2 squared plus 12. What do we ultimately get? Well, you have a positive times a negative, right? Or in this case, we're probably going to have to know, we're going to have to figure out the values right there. This is 4 times negative 12, that's negative 48, plus 12, that is a negative number, right? So we know that we are having a concavity or concave down in this first region. What about at x equals 0? Well, if we plug 0 in, you get 0 squared is 0 times negative 12 is 0 plus 12 is 12. That's positive. So we know we're going to be concaving up between negative 1 and 1. If I choose something bigger than 1 for the third region, like x equals 2, then we have negative 12 times 2 squared plus 2. And then we get 4 times negative 12 that's negative 48 plus, this is a 12. And we get a negative, right? If you really want, you could say, oh, it's negative 36. But this is what matters, right? That it's negative. So now where's it concaving up and down from? Well, it's concaving up with the plus region, right? So where is that happening at? Between negative 1 and 1. Where is it concaving down at? Well, in the first and the third region. The smallest value that it begins to concave down from is negative infinity. Until what x value? Negative 1. Where else does it start to do that? At positive 1, right? And it concaves down towards, or keeps concaving towards x equals positive infinity. Do we have inflection points right here? Yes, we do, right? Remember, inflection is where you have sign changes between these derivatives, between the second derivative critical values. So notice how we went from minus to positive, right? And then positive to negative. These are inflection points right here. But yes, at x equals negative 1 and 1. And again, it's because we went from negative to positive or positive to negative, right? So we need to figure out what are those y values going to be? What are those respective y values? So we need to take these values and plug them back into the original function, which was this right here. So f of negative 1 equals, again, watch the sign, right? You got that negative on the outside, negative 1 to the 4th, plus 6 times negative 1 squared, plus 18. That gives you, what's that give you? 23. So at negative 1 comma 23, that's where you have your, or one of the inflection points. The next one happened at 1, right? X equals 1 because we were going from positive to negative with the test for concavity. And you also get 23. So that point's going to be 1 comma 23 in this instance. All right, so let's try another. Let's try 12. All right, so x to the 3/7 right here. So first, got to find that first derivative, right? F prime of x. What is that going to be? 3/7 x to the negative 4/7, right? Because you're going 1 minus that right there. So this is like saying 3/7 x to the 4/7. And if we want to find the critical values, what do? We take it and we set it to 0, right? So what do? Remember, you have a rational expression, right? So you set the top to 0 if it had an x, and the bottom to 0 if it had an x. So in this case right here, we just have 7x to the 4/7 equals 0. But where is that true at? Just 0, right? So remember what we're doing now with this first derivative, that's going to tell us intervals on which it's increasing and decreasing, right? So in our first region, we can test -1. And then for the second region, we can test x equals 1. When you plug that in, we have 3/7 -1 to the 4/7, right? Be careful right here. What does -1 and the 4/7 give us? It doesn't give us a negative number. Remember what this is this is like saying the 7th root of -1 to the 4th power, okay? Remember, fractional exponents are just radicals. This is the 7th root of -1 to the 4th. What's the 7th root of -1? It's not imaginary, it's -1. What's -1 to the 4th? It's +1. This is +3/7 right here. So in the first region, it's positive. What about in the second region? This is 3/7, and then we have 1 to the 4/7. Guess what? This is just +1. This is +3/7. So this is plus. So look, it's both plus and plus right here. What does that tell us? That there is no local max or no local min, right? Because there's no transition from positive to negative or negative to positive. So no local extrema. Okay. So since we have that, what's the next thing we need to talk about? Where is it increasing and decreasing from? Well, we can see that it's not decreasing, right? Because do we see any negative signs right here? No. So I'm just gonna put none right here. What about increasing? Where is it increasing from? Well, we have 2 pluses, right? Be very careful though. We can't say, oh, from -infinity to +infinity, because that means you're including the 0. What's the problem with this 0 right here? Well, when you plug the 0 into our function, remember what's happening right here. If you plug 0 and you get 0 in the denominator, which is undefined, right? So you have to be careful with that. So what does that mean? We have to basically stop at 0 just before and then pick up again with it, meaning we are increasing from -infinity to 0, and then again from 0 to infinity. Again, the reason why I can't include the 0 is because this 0 came from the denominator as a critical value, right? So you have to be careful with those denominator x values that make the bottom 0, because that causes it to be undefined. So we cannot include that right there. So that is increasing, decreasing, and the extrema. What about the concavity, right? So now we need to find the second derivative. We'll work off this one right here. What is that? If we do the power rule, it's -12/49, and then x to the -11/7. So we're multiplying 3/7 times -4/7 to get that. -4/7 minus 1 gives you -11/7. This I'll just rewrite as this. I'm gonna make that exponent positive, right? So now what if we take that and set it to 0? Well, just like the last one, right? You set the top to 0 and the bottom to 0 if they have x's. Only the bottom has an x to solve for. but that this one is just x equals 0. So now we're going to draw our little test point and the regions. In this case right here, I'll test -1 and I'll test +1. If I plug -1 into this expression, we get -12 over 49 and -1 to the 11/7. This is not going to be +1, okay, like it was for the first derivative. This is going to be negative. If you're in doubt with that, throw that into the calculator. Say -1, caret key 11/7, hit enter, and it's going to spit out -1. So basically, we have -12 over -49. That's positive, right? What if I plug 1 in? We get -12 over 49 and then 1 to the 11/7. Well, that's -12 over 49, which is negative. So what? Okay, we'll go over here. So as far as concave up and concave down, we do have that in this case, right? We have a plus region. So we are concaving up from -infinity to 0. And then we are concaving down from 0 to what? Well, forever to the right, which is +infinity. Do we have an inflection point? Yes, right? Because you have a transition in the signs, the second derivative, positive to negative. So inflection at x equals 0. But we need its y value, right? We need the whole entire point. So we need to find f of 0. So we go back to the original function. Well, that's pretty easy, right? It's just 0 to the 3/7, which is 0. So your answer is 0, 0 in that case. All right, let's try. We'll do 11. And for practice, you can do 13 and 10. So for 11, we have f of x equals x plus 2 sine of x. And it's limiting us from 0 to 2 pi, right? So what do we start with first? First derivative. What's that derivative going to be right there? Well, that's just going to be 1 plus 2 cosine of x, right? So where do we go from here? Set it to 0, right? So we have now cosine of x equals -1/2. Where's that happen at? Well, you got to go to that wonderful unit circle, right? That's actually happening right here and here. This is -1/2, comma, square root of 3 over 2. This is -1/2, comma, negative square root of 3 over 2. So remember, if you need to go back and look at that review, right? The trig review on Canvas, or just look up something, Paul's online notes on Google. So where's this happening at? At x equals 2 pi over 3 and 4 pi over 3. So we have 3 regions, right? 1, 2, and 3 right here. So what are some nice test values that we can use between these regions? Well, between 0 and 2 pi over 3, why not use this one right here? What is that? That is just pi over 2. What about between 2 pi? This is 2 pi over 3, and this is 4 pi over 3. What's something nice between there? Pi, right? This. And something nice between 4 pi over 3 and 2 pi between here and here, right? We could use 3 pi over 2. So let's plug these values in, right? Where are we going to plug them into? The first derivative. And we want to see, do we get a positive result or a negative result? So this is 1 plus 2 cosine of pi over 2. So that's 1 plus 2 times, and what's cosine of pi over 2? All right, so 1 plus 2 cosine of pi over 2. Well, what is cosine of pi over 2? Remember, this pi over 2, right? This is going to be 0. So we get 1. What matters, though, is that it's positive. If you want, you can throw these values into your calculator, right? Make sure you're in radian mode. Now moving on to the next piece, right? What if we plug pi in? We get 1 plus 2 cosine of pi. This is 1 plus 2 times, what's cosine of pi? That's 0. Oh, I'm sorry, that's not 0. That's negative 1. And then this is 1 minus 2, which is negative 1. So that tells us that the second region is going to be negative or decreasing right there. Let's go on to the last one. We have 1 plus 2 cosine of 3 pi over 2. This is 1 plus 2 times, what's cosine of 3 pi over 2? 0. So you wind up with just 1, which is positive right there. So now we have that. We can determine where we're increasing and decreasing from. So increasing, we have a couple regions, right? From 0 to 2 pi over 3. And then also 4 pi over 3 to 2 pi. What about decreasing? Sure do, right here, right? Second region, what are those x values? 2 pi over 3 to 4 pi over 3. Do we have local maxes and mins or local extrema? We do, right? Because look, we have transitions from positive to negative, negative to positive. So remember right here, this is going up then down. Right here, this is going down then up. So where do we have a max at? Where it's opening up, right? At x equals 2 pi over 3. So y would be f of 2 pi over 3. So remember, we plug that back into the original, right? So that's 2 pi over 3 plus 2 sine of 2 pi over 3. What is that? That's 2 pi over 3 plus 2. What's sine of 2 pi over 3? Well, if you go to the unit circle, it's going to be the square root of 3 over 2. So these cancel out. So your answer would be 2 pi over 3 plus square root of 3. As a point, right? As a point right here, the max. That's 2 pi over 3 for the x. The y value is 2 pi over 3 plus root 3. That's this chunk right here. Where's your local min at? It's right here, right? We saw that at 4 pi over 3. But what's that y value going to be? Y is going to be f of 4 pi over 3, which is just 4 pi over 3 plus 2 sine of 4 pi over 3. That's 4 pi over 3 plus 2. And then it's going to be negative square root of 3 over 2 instead. These 2's get knocked out. So then you're left with 4 pi over 3 minus root 3. As a point though, right? As a point, that's going to be 4 pi over 3, comma, 4 pi over 3 minus root 3. So that's just the local extreme and increasing and decreasing. We still need to do concavity, right? So let's go and take the second derivative. What is the second derivative of this going to be? It's going to be negative 2 sine of x. Okay, so we take that and set it to 0. We get sine of x equals 0. Where's that happening at between 0, 0, and 2 pi? It's only happening at x equals pi. So this one's a little shorter, right? So only 2 regions to play with. So remember, we're trapped between 0 and 2 pi. We have to choose something between these. Right here, what works is pi over 2. And right here, we can use 3 pi over 2. So if I do sine, right, if we go back to our second derivative, which is negative 2 sine of x, remember that's our second derivative. What happens when we plug that in? We get negative 2 sine of pi over 2. Sine of pi over 2 is 1 times negative 2 is negative 2. So it's negative within the first region. What about this one? So if we do that, negative 2 sine of 3 pi over 2, that's negative 2 times negative 1, which is 2. That's positive. All right, so we figured that out. So we do have concave up and down. Concave up at pi to 2 pi, and concave down from 0 to pi, like that. We have inflection. I'll just put INF. Inflection at pi, right? Why? Because you have a change in sign in the concavity. What's the value where this is happening at, though, with respect to y? So y is equal to f of pi. What is that? That is pi plus 2 sine of pi. What's sine of pi? 0. So this is pi plus 2 times 0, which is pi. So your inflection point, this as a point, is x is pi, and y is also pi. Okay? So yeah, these seem long because, again, we're finding the first derivative, setting it to 0, getting its critical values, testing points around them, and all that stuff, right? Seeing where it's increasing and decreasing. And then you're running through all that. Then you have to take the second derivative and do it all over again, right? And run it through the same types of procedures. But remember, as you're doing it, just take your time, right? Because it's a lot. I know it's a lot, right? Look how long it's taking to do one problem. It's a lot, even if you know what you're doing. So just take your time. It's not a race, okay?